Hi friends, welcome to BHK Electrical Concepts. So myself Budida Harikrant, working as assistant professor in ACE Engineering College, Hyderabad. So today in this video I am going to discuss about the concept of torque equation of a three-phase induction motor. So in my previous video I already discussed about the concept of synchronous speed and also the concept of slip, as well as what is the value of slip under the standstill condition of a rotor and what is the value of slip under the running condition of a rotor, because these all topics are required to understand for getting the torque equation. Clear? So that is the reason why. So you must watch my previous video for better understanding how we are getting the torque equation for three-phase induction motor. Clear? So here torque is always directly proportional to E2 I2 cos pi 2. Okay, so torque is directly proportional to E2 I2 cos pi 2. Here E2 represents the EMF generated in rotor, and the value of I2 represents the rotor current, and cos pi 2 represents the power factor of rotor. Okay, so E2 represents the EMF generated in the rotor, I2 is the rotor current which is flowing in the rotor circuit, and cos pi 2 is the power factor of the rotor. Clear? So how we are writing this torque expression? Torque is directly proportional to E2 I2 cos pi 2. How we are writing this expression means based on the working principle of a three-phase induction motor. So we are writing this expression. Clear? Now coming to the most important one, that is, so whenever we are going to discuss about the concept of torque, so here this torque is, we are going to get this torque under standstill condition, of rotor, and the second one is a running condition. Okay, it means what? In case of three-phase induction motor, so we have two different types of torques are there. One is torque with the help of rotor at standstill condition and torque under the running condition of a rotor. Clear? So we are going to get the torque expression for standstill condition of rotor as well as running condition of a rotor. But what is standstill and what is the running condition of rotor? So about these two, I already explained about these two in my previous video, and the video is available in this description, video description. Clear? So you can go to description of this video, so you will get the link of my previous video. Clear? So now standstill condition of rotor and running condition of rotor. Clear? So once again I am explaining here. Standstill condition means the rotor is at rest. Means the speed of the rotor is always 0 rpm. Okay, and what is a running condition? Running condition of rotor means rotor is rotating with some value of speed. Okay, so that is the reason why definitely the value of speed is not equal to 0. Okay, not equal to 0. For example, I am considering, for example, 1500 rpm or 1600 rpm or 1000 rpm or 900 rpm, like this. Okay, so we can directly, with the help of tachometer, while you are conducting experiment on three-phase induction motor, with the help of tachometer you can directly get the speed of the rotor. Okay, so this is about what? Standstill condition of a rotor and running condition of a rotor. What is the value of speed of a rotor? Okay, so these two values, that is what? N is equal to 0 under standstill condition, N is not equal to 0 under running condition. We require these two for getting the value of torque. Okay, so, and I already explained about the most important point, that is what is the value of slip under standstill condition and what is the value of slip under running condition. Okay, so here under standstill condition, standstill condition, the value of slip is always 1. Okay, the value of slip is always 1. How we are getting the value of s is equal to 1 means by using the expression of slip, that is ns minus n divided by ns. Okay, so you know that under standstill the value of n is 0. So that what? Ns minus 0 divided by ns. So that what? Ns divided by ns. It means you are getting the value of s is equal to 1 because we are talking about standstill. Okay, so that is the reason why the standstill condition of rotor, the value of slip is always 1. Okay, now what is the running condition? So under running condition of a rotor, the value of slip is always not equal to 1 as well as not equal to 0. The value of slip is, we are getting the value of slip is always between the range, that is 0 to 1, like 0.8 or 0.6, 0.5 or 0.4, like this you are getting. Otherwise you can also get 0.02, 0.04, like this you will get under running condition of a rotor. Clear? Because slip is equal to ns minus n divided by ns. For example, the speed of the rotating magnetic field, for example, I am considering as 1500, and the rotation of the rotor, for example, at for example 1400, then so 1500 is equal to what? You are getting 100 divided by 1500. So here 2 zeros and 2 zeros we are cancelling. So 1 by 15. It means what? You are getting the value of slip between 0 to 1, in the range of what? 0 to 1. So that is the reason why under running condition of a rotor, slip is always not equal to 1 as well as not equal to 0. Okay, you are getting in between the range what? From 0 to 1. Clear? So now our target is to get the torque equation under the standstill condition of a rotor as well as under the running condition of a rotor. Clear? And the most important point is I already discussed about the rotor frequency. Okay, so the rotor frequency under standstill condition. Okay, the rotor frequency under standstill condition is always, it follows the supplied frequency. It means what? Under standstill condition of a rotor frequency is exactly is equal to supplied frequency. But under running condition, rotor frequency is equal to slip times the supplied frequency. Okay, so that is the reason why. So under running condition of a rotor frequency is equal to slip times the frequency, and under standstill condition of a rotor, the rotor frequency is equal to supplied frequency. Okay, so with the help of all these values, now we are going to get the torque equation for standstill condition as well as running condition. Okay, now see here, this is most important equation for 3-phase induction motor. Clear? Now just see here, first thing I am going to get the torque equation. First I am going to get the torque equation under standstill condition. Okay, so under standstill condition of a rotor means what? Rotor do not have any speed. It means what? Standstill means constant, it is not rotating. So the torque equation under standstill condition, so you know that under standstill means the rotor speed is always 0 rpm, and under standstill the value of slip is always 1. Clear? Now coming to the torque expression, torque is directly proportional to E2, I2 and cos pi 2. You know that E2 is the EMF generated in the rotor, I2 is the rotor current which is flowing in the rotor circuit, cos pi 2 is the power factor of the rotor. So but what is the value of rotor current, and what is the value of E2, and also what is the value of cos pi 2? So to get all these values, first we need to go for the equivalent circuit of a induction motor. So what is the equivalent circuit of induction motor, which is same as that of the transformer? Okay, so here this is R1, for example, this is X1, and we are applying some value of V1 voltage, and here for example E1 is the generated EMF in the primary, and here this one is secondary side equivalent circuit. So this is R2, this one is X2, and EMF generated in the rotor side is E2, and for example we are connecting, so one load here, for example I am connecting load here. Okay, now with the help of V1 the value of I1 will flows, and with the help of the EMF generated in the rotor the value of I2 will flows. Okay, like this. Now go for the concept of what? Now go for the concept of, sorry, go for the expression of I2 and cos pi 2 and E2. Okay, now see here. So EMF generated, okay, EMF generated in rotor. So EMF generated in rotor under standstill condition. So what is the value of E2 under standstill condition of a rotor means, you can observe here E2 is equal to slip times the E2, but you know that under standstill condition of a rotor S is equal to 1. So that by placing the value of 1 here, so you are getting again what? E2. So that is the reason why under standstill condition of a rotor the EMF generated in the rotor is always E2 is equal to E2 only. Okay, so this is clear. Now coming to the second one. What is that second one? Current I2. Okay, current I2. And before I am going to write the expression of current, I will show you the most important condition. So you know that under standstill condition of a rotor the value of S is equal to 1. So that you are directly placing the value of 1 is equal to S in this expression. That is the reason why you are getting like this. But under running condition, the value of S is not equal to 1 and S is not equal to 0 means you are getting some value of slip from between 0 to 1. So that whenever you are going for the expression of E2 under running condition, so it will becomes what? E2 is equal to S into E2. Okay, so this equation we need to consider under the running condition of a rotor. Clear? Now go for the I2. Now see here I2. Here I2 is equal to I is equal to V by R. So I2 is equal to here E2, that is EMF generated in the rotor is E2, and here R2 plus JX2. It means that what? The combination of resistance and reactance gives a value of impedance. So that I2 is equal to E2 divided by Z2. Okay. Now here you can directly write here I2 is equal to E2. E2 is always same. E2 is equal to E2 in case of standstill, because S is equal to 1 under standstill condition. So that I am directly placing the value of E2 as it is. And coming to the Z2. Z2 is what here? The combination of the rotor resistance and reactance. Rotor reactance, it will give the value of Z2. So whenever we are writing the expression of Z2, you can always write under root R2 square plus X2 square. Clear? So here I2 is equal to E2 divided by under root R2 square plus X2 square is the expression of I2 under what? Standstill condition. For example, if I am going to write the expression of I2 under running condition, then what are the changes occurred in this expression? So instead of E2, you need to place S into E2, and here R2 square plus, instead of X2 square, I need to place S into X2 square, because rotor frequency, just you can observe here, because here rotor frequency under the running condition is what? S times the frequency, S times the supplied frequency. So that is the reason why when you are going to discuss about the rotor under running condition, you always multiply slip to the all frequency components. So that what? So here X2 is what? X2 is a frequency component. So that I need to multiply S to the X2. So that S into X2 square. So I think you are getting doubt. How we can say that X2 is a frequency component? Because X is equal to omega L. So omega is 2 into pi into F. So here F is frequency. So that whenever we are talking about the induction motor under running condition, okay, under running condition, you always multiply slip to all frequency components. So because of that reason only, I am multiplying S to the X2 term, and here E2 is also frequency component. So that is the reason why I am multiplying S to the E2. Okay. So now coming to the expressions of I2 under the a running condition as well as what standstill condition. So just now we already written, again I am writing here, just you can observe here. So here the rotor current, here the rotor current, here the rotor is under standstill condition. So standstill condition. So under standstill condition, what is the rotor current? Rotor current is at I2. So under standstill condition, I2 is equal to E2 divided by under root R2 square plus X2 square in amperes. And for example, if the value of rotor current under running condition, you can directly write I2 is equal to S into E2 divided by under root R2 square plus S into X2 square in amperes. Okay. Now equation of I2 for standstill condition and running condition is also over. Now what is the third term? That is cos pi 2. Okay. So here cos pi 2 is what? The power factor of the rotor. So in case of induction motor, if you want to define the definition of power factor, you can directly define like this. So cos pi 2, that is what? Power factor of rotor is defined as the ratio of rotor resistance to the rotor impedance. Okay, so that is the reason why I am writing cos pi 2 is equal to reciprocal of rotor resistance to the rotor impedance. Okay, is called as the power factor of a rotor. So here R2 divided by, so Z2 means what? Z2 is R2 square plus X2 square. Okay, so R2 divided by Z2 means under root R2 square plus X2 square. So if this expression is under standstill condition, you can directly write like this without multiplying S2 X2 term. But in case of running condition, you can directly write the cos pi 2 expression, that is R2 divided by Z2, so that you can directly write R2 divided by under root R2 square plus S into X2 square. Okay, you can observe here most important point, under running condition of the rotor only we are multiplying slip to all frequency components, but under standstill condition we are not multiplying slip to all frequency components. Okay, so now you know that you got the E2 expression for standstill as well as running condition, and you know the expression of I2 for standstill as well as running condition, and you know the expression of cos pi 2 under standstill and running condition. Clear? Now we are going to write the equation for torque. Okay, so you know that torque is directly proportional to, so E2 I2 cos pi 2. Okay, so for example, what I am doing, I am starting with the torque equation for standstill condition first, and after that I am going to discuss about, or I am going to derive the derivation of torque equation under running condition. Okay, so you have to remember this expression for getting the torque equation under standstill as well as running condition. Okay, now see here, this is the most important equation, and with the help of this equation we can easily understand the operation of complete induction machine. Clear? So now here torque equation of three phase induction motor at standstill condition. Okay, so torque equation of three-phase induction motor at standstill condition of rotor, most important. Okay, so now you know the conditions required, and you know the conditions of all slip, speed as well as current equation, cos pi 2 expression and E2 equation. With the help of all these things we can easily get the torque equation. Now you can observe here, so torque is Torque is directly proportional to E2 I2 cos pi 2. Okay. Now in order to neglect this directly proportional constant, directly proportional, so I'm going to write T is equal to, here K represents the proportional constant, I'm writing here, into E2 I2 cos pi 2. Okay. Now here T is equal to K as it is placed here. Now we are talking about standstill condition of a rotor. It means that what? E2 is always E2 only. We are not multiplying slip to this particular E2. Okay, because we are talking about standstill. So T is equal to K into E2. And what is the expression of I2? I2 is equal to E2 divided by under root R2 square plus x2 square. And what is cos pi 2 under standstill condition? That is R2 divided by R2 square plus x2 square. Okay, now you can simplify here. So K into E2 means E2 square into R2 divided by, so under root R2 square plus x2 square, under root R2 square plus x2 square. It will give the value of what? So R2 square plus x2 square. Clear? So here torque is equal to K into E2 square into R2 divided by under root R2 square plus x2 square. Now here K represents the proportional constant, and the value of K in case of three-phase induction motor for a torque expression, we can always write 3 divided by 2 pi ns. Okay, so this value is the value of K for the torque equation of three-phase induction motor into, so E2 square into R2 divided by R2 square plus x2 square. Okay, so you can directly write, so torque equation of three-phase induction motor at a standstill condition of a rotor. Standstill condition of rotor means what? Initially rotor is not rotating, so that time we are getting torque. So that is the reason why we are calling as starting torque. Okay, so starting torque. So T starting means starting torque. So this torque expression is given by, so 3 divided by 2 pi ns into, so E2 square into R2 divided by, so R2 square plus x2 square. So what is the unit of torque? Torque is always Newton meters. Clear? So this expression, okay, so this expression gives the starting torque of a three-phase induction motor. Okay, so starting torque of a three-phase induction motor. But when the starting torque is maximum, okay, at what condition the starting torque is maximum? So the value of torque is always maximum under starting when the value of R2, that is rotor resistance, is equal to, so rotor reactance. It means what? So when the value of R2 is equal to x2, then the starting torque will be maximum. Okay, it means that instead of R2 you can directly substitute x2, or instead of x2 you can directly substitute R2. So with the help of substitution of this particular condition, you are getting torque. That torque expression gives the maximum starting torque. Clear? But how we are getting this expression, or how we are getting this condition? Okay, so how we are getting this condition? So for that I need to prove this condition with the help of this starting torque expression. Okay, so you can observe here, I'm clearly explaining so how we are going to get the starting torque. Clear? So here now you got the starting torque. Now you got the starting torque, that is equal to 3 divided by 2 pi ns into E2 square into R2 divided by, so R2 square plus x2 square. Now assume this is equation number 1. Clear? So whenever we are going to getting the condition required for getting the starting torque of three-phase induction motor, so what we need to do? We need to consider only the parameters R2 and X2. Okay, R2 and X2, and this term represents the constant. So that, so here starting torque is equal to K into R2 divided by R2 square plus X2 square. Okay, why I am not considering the value of E2 square means E2 is always fixed. Okay, E2 is always fixed in any induction motor. So that what? So I am neglecting this E2 square in the equation number 1 for getting the condition required for getting the maximum starting torque expression. So that is the reason why. So I am considering this as equation number 2. Now what we need to do? I need to differentiate equation number 2. Differentiate equation number 2 with respect to R2. Okay, so differentiate equation number 2 with respect to R2 and make it is equal to equal to 0. Then this time you will get the condition required for maximum starting torque. Okay, so now that is the reason why. So equation number 2 is this one. So I can directly differentiate, that is d starting torque divided by dr2, because I am differentiating with respect to r2, so that I am taking common k here. So here d divided by dr2 of r2 divided by r2 square plus x2 square. Okay, now this is in the form of what? U by v. Okay, now this is in the form of u by v. U by v formula. What is the formula of u by v? You can directly write u dash v minus u v dash divided by v square. It means that what? R2 is u, denominator is v. So by applying this formula to this, then you will get what? So k into, so u dash means u dash is what? R2. With respect to R2 means you will get 1. And what is v here? V is what? V is denominator, so that I am directly writing instead of v. So R2 square plus x2 square minus u. U is what? U is 2. And v dash is R2 square plus x2 square. But we are differentiating with respect to what? With respect to R2. So that you will get what? So 2 times of R2 divided by, so R2 square plus x2 square whole square, because v square is the denominator term, and make it is equal to 0. Clear? Now see here. So d starting torque divided by dr2. So this term is equal to, so now we are making equal to this term is equal to 0, so that you will get what? So here 1 into r2 square plus x2 square means, so r2 square plus x2 square. Here this k is moving to that side, it will become 0, because 0 divided by k means 0 only. So minus 2 into r2 square means 2 times of r2 square divided by, so r2 square plus x2 square is equal to 0. Okay, so from this we can directly write, so this r2 square plus x2 square denominator term is going to multiply the 0, that this denominator is going to that side, then 0 into this denominator means you will get what? 0 only. So that is the reason why r2 square plus x2 square minus 2r2 square is equal to 0. So here minus 2r2 square and 1 plus 2r2 square, it will becomes what? So x2 square minus r2 square. So that from this, by simplifying, you will get what? By simplifying you will get, so you will get what? R2 square, just see here. So finally you got what? X2 square minus R2 square is equal to 0. From this we can directly write what? So x2 square minus R2 square is equal to 0. So from this I can directly write x2 square is equal to, so R2 square. So here directly write x2 is equal to R2. So this is the condition required for getting the value of what? Maximum starting torque of 3-phase induction motor. Okay, now you can write here, what is the equation number 1 here? The equation number 1 is, 3 divided by 2 pi ns into E2 square into R2 divided by R2 square plus X2 square. Clear? So this is equation number 1. Now what I am doing, I am going to substitute R2 is equal to X2 or X2 is equal to R2 in this expression. Then the equation will becomes maximum starting torque. So that T is equal to 3 divided by 2 pi ns into, so E2 square into, what I am doing, simply I am substituting, instead of R2 I am substituting, for example, X2. Clear? X2 divided by, so R2 square means what? X2 square plus X2 square as T is I am substituting here. So that T is equal to 3 divided by 2 pi ns into, so E2 square into X2 divided by 2 times of X2 square. Okay, here numerator consisting of 1x2 and denominator I am cancelling 1x2 here. Then it will becomes what? So 3 divided by 2 pi ns into E2 square divided by 2x2. Okay, so from this I can directly write T is equal to, so this I am substituting R2 is equal to X2. It means that what? This torque represents what? Maximum starting torque. Clear? So that is the reason why. So maximum starting torque is equal to, so 3 E2 square divided by 2 into 2 means 4, and remaining pi is already there, and ns is already there, and X2. Clear? So this expression gives the maximum starting torque. Clear? So most important expression. So this is the maximum starting torque of a 3-phase induction motor. Clear? If you know the concept of synchronous speed of rotating magnetic field, slip of 3-phase induction motor, and what is the difference between standstill condition and running condition, and what is the value of slip for standstill condition and running condition, and what is the value of speed under standstill condition and running condition. If you are clear with all these terms, then only you can easily understand how we are going to get the starting torque expression as well as maximum starting torque expression. Okay, so in the next video I am going to derive the derivation of torque for running condition of a rotor. Okay, so under running condition of a rotor, what is the expression of running torque, and what is the expression of maximum running torque? Okay, so that equation I am going to discuss in the upcoming video. So please do subscribe my channel for more updates. Thank you.